Okay. Hello. This is Lab 8 for Group 6. The lab we're doing for is improved biasing circuits. I'm Shane.
I'm Daniel Rubio.
Mark and Junior, they couldn't join us because they had other obligations to do. One had work, or both had work, and other things that had to come. They did contribute, but we will be going without them. Okay.
The objectives.
Go ahead.
The objectives is to explore, verify basic characteristics of improved base circuit using the polar junction translator, for short BJT, to plot the gain amplifier, the function frequency, and to understand the couple frequency response in different parameters, and to test the DC and AC characteristics, the source of the special bias configuration for the BGT common emitter amplifier, COO3.
This is activity 1, the diagram. What we're going to do. We have to find for A. We gotta find the I2, IB, BR2, VCC, VRE, which equals approximately to VCC. VLC will equal to VCC, and IC equal to 2MA. We have to find the values of R1, R2, RE, RC, VCC. We have to find the proper requirements. We have to measure the VL2 and connect the we have to connect transistors and remove the transistor to see how it works. We also find the RC, which equal to 0 ohms, and RC that equal to 100 ohms. This is activity 1, and now we shall show our calculations.
This is the calculations based on activity 1, where, as you can see, we have I2, the formula VCC over R resistor 1 over R2 plus R2. It gives us the resistor, the value of 1K ohm for the second resistor, and the first resistor is going to be twice value as that. It will be 2K ohms. Now going to the right, we have VCC 8.4 volts based on the calculations done above. And we have RE 1.05K ohms. Given the calculation to calculate that, it's on above. We have RC 1.4K ohms. And VR2 with the value of 2.8 V. And on the left bottom corner, we have IC 2MA for the current, VCE 6.3 volts, IC 2MA for the current, and AC we have 6.1 volts. As you can see, these are the calculations.
This is the MyDoc setup for activity 1. I'm not sure if you can really see it clear, where we use, like in the calculation, we had 1K resistor with 2 of them. We had 1 resistor for 2K, 1 resistor for 3K, and we had a VC ground that helped the voltage move around the circuit.
This is the multisystem, where we have on the left side, the transistor. We have RE with a value of 1.90K ohms. A little bit to the left, we have R2 resistor, 1.6K ohms. It goes through the DC source, 10 ohms, with a value of 4.882 volts for VR2. Above that, we have R1, the resistor, 3.3K ohms. And On the right side, we have RC, 2.5 k ohms. And we have the ground located in VC with a value of 15 volts. And on the right side, we have the node translator. We have the source DC with a value of 4.897. 10 ohms is the measurement. VR2. Resistor 2 is 1.6 k ohms. Resistor 1 will be 3.3 k ohms. RC will be 2.5 k ohms. On the bottom, we have RE, a resistor, 1.9 k ohms. And for the ground, looking on the above right corner, DC, the value is 50 volts.
Also to add, as you can see how the left side has a transistor and then the right side doesn't. You look at our VO2s, it barely makes a difference in our calculations. VO2 is 4.882 and VO2 on the right side is 4.897. Let's put it out there. Moving forward. This is activity 2, the diagram and our calculation, since we have most of it in part 1. As you can see, on the left side, the question is the circuit for part 2. As you can see, you had to go back to part 1 to set up the following circuit. So it's somewhat similar. Our IC is 2 mA. Our VCC is 8.4 V voltage. Excuse me. Our VCE is equals to 6.3 voltage. Our VC is 5 voltage over 12. 5 voltage CC over 12. And our VCC equals to 5.4 voltage. R equals to 2R2, with equals to 20 k ohms. And VO2 is 10 k ohms over 30 k ohms times 3.5, which equals to 1.16 voltage.
This is the MIDAP with the multisome for activity 2. On the left side, we have the graph increasing over frequency, hertz. On the vertical side, the y-axis, we have the gain. As you can see, they're almost proportional, slightly curved upward to the right side. On the red line, we have a decrease, a falling decrease, where near that location we have a slightly increase going to constant motion. For the bottom, we have the results going decreasing to almost 0. As you can see, a decrease. No, I'm sorry. The value went to negative value, almost touching the 200 for phrase, around 5K frequency hertz. On the right side, similar to activity 1 or multisome, but slightly different. We have the same DC, 10 megavolts with a value of 4.883 volts. Same units for the resistor, 3.3 k ohms and 1.6 k ohms, 190 k ohms. The 2N3904, the amplifier. On the right corner, where appears to be different, we have the VCE, the 10.8 volts, another source, DC. And on the right side, we have the measurement to 0.199 mA, the current. You see the functional multimeter that measures the resistor of VC, which shows us 0K ohms to the amplifier Q1, 2N3904.
Okay, go forward. This is still multisim, but this is the graph. As you can see in the left side, how we have channel A and channel B. They're both, like I say, they're constantly in a decrease and an increase going across the graph. The scale of time base is one millisecond. The channel A is 5 voltage, channel B is also 5 voltage. As you can see with the graph to the right, is going to be our magnitude. As you see how it start to increase at a constant rate, this stumbles a little bit at a constant, then slowly curves and slopes up back to a constant and starts to decrease going on.
This is activity 3, schematic diagram with calculations. We have IC equals to MA, the current, VCC, 8.4 volts, VCE, 6.3 volts, VCE equals to 5 VCC over 12, where we have VC equal to 5.4. The first resistor, R1, equals to 2 R2, meaning is twice as the value. We have the value to be known as 20 k ohms. VR2, we have 10 k ohms or 30 k ohms times 3.5, giving us the result of 1.16 volts.
And also to add, if you look at the top, it says when it says number 3, it says that we repeat part 2 for the following setup. So that's why our calculations is not exactly different. It's almost the same, just to let you know. This is my doc and our multi-sim. Our doc to the left and multi-sim to the right. As you can see, as in activity 2, as Daniel mentioned, it looks similar, but not exactly. On the left side, using my doc, you see our frequency, our hertz. It starts at, you could say 5.5, and the gain starts at 5.5 at 5.0 to be around 5.0.5.5, and it starts to increase as you can see when it starts to hit, when it increases all the way to, you can say that negative 2.0, it stops increasing and starts to go at a constant rate and starts to slopes and curves. So at 1.5, it increases a little bit and stay constant. And as you get end, you can see it starts to decrease when it hits 10,000 frequency hertz. And the bottom for that, which is the phase, it starts at, you could say maybe 52.5 and starts to decrease, not at a constant rate, but at maybe you could say at 600 frequency hertz, it starts to steady itself and curves upward, but not curve upward, but starts to curve and I guess concave itself, and it goes at a constant rate when it reaches to maybe you could say at 9,000, it spikes up and starts to increase. To the right side is the multisim. Not exactly too different from the step before, but we have 1 equals to 3.3 k ohms. Capacitor is U mu F. R2 is 1.6 k ohms. RE is 1.9 k ohms. RC is 100 ohms. Our VC is 15 voltage. And our VCE, it says 10.577. And our DC is 10 milliohms. And our VN is 5 voltage PK with 1 k hertz.
This is activity 3, multism. The graph on the left side, we have a slope going a constant speed upward proportional, where we have y equals x, right about in 3/4 of the graph, we have a constant speed going to 0. And in the right side, we have channel A at 2.808 volts, and channel B, as you can see, it's not. As you can see, it falls under 10 volts. But between 0 volts and 10 volts, not much a difference. Gives us the value of 7.652 volts, where you can see the graph is slightly almost the same as it replicates the sine function. But the difference will be the frequency amount to travel.
Okay. And in conclusion for this lab, we had examined and verified the working of BJT in all the configuration of the common emitter, common collector, and a common base amplifier. In part 1, we found that disconnecting the transistor did not greatly affect the current running through the 2 resistors in R1 and R2. And also, in this lab, we also learn and analyze that if there is no change in the input stage, that is IB will not change. Hence, no change occurred in the IE. The impact of placing the impact of placing the co-looping capacitor. And that is all of our labs. I mean, not all our labs. That's it for this lab, for lab 8. Again, this is Shane, Mark, and Daniel. Mark and Daniel could not participate in this lab because he had other things, other responsibilities to attend to, but it did contribute in some parts of the lab. The time is around 11 o'clock. Thank you, Professor.
Thank you.
Have a good day. Okay. That's the end of that. Now we gotta wait till the shit fucking